and a warm welcome to one and all over here with you. I am Disney, a faculty of the Department of Mathematics. It's the ninth day of the international webinar series on various fields in mathematics organized by the Research and Postgraduate Department of Mathematics in association with IQAC Maharaja's Government Autonomous College, Ernakulam. Today, we have with us Dr. Manoj Kummini, Associate Professor of Mathematics, Chennai Mathematical Institute, to give a talk on group actions and some applications. Let me invite Dr. Vinod Kumar Kallolikal, CDC Coordinator, Maharaja's College, to speak a few words. Sir.
Hello.
Vinod sir.
Sorry.
Okay. Now we have the felicitation talk.
Bahumanapada Maths HOD, Dr. Blumey Joseph, the National Webinar Coordinator, Jismeri Madam, അതുപോലെ വെബിനാറിന് ആശംസ പറയുന്നത്. അതിൻ്റെ പ്രധാനപ്പെട്ട കാരണം ഹിസ്റ്ററി ഓഫ് മാത്തമാറ്റിക്സ് എൻ്റെ ഒരു പ്രധാനപ്പെട്ട വിഷയമാണ്. ഞാൻ ഈ മഹാരാജാസ് കോളേജിൽ വന്ന ശേഷം ആ രീതിയിൽ ഒരു ബുക്ക് പോലും ഞങ്ങൾ പബ്ലിഷ് ചെയ്തിട്ടുണ്ട്, അഡ്രസ്സിംഗ് ഹിസ്റ്ററി എന്നുള്ളതാണ്. അതുപോലെ ചെന്നൈയിലെ അല്ലാട് രാമകൃഷ്ണൻ സ്ഥാപിച്ച മാത്സ് സയൻസുമായി എനിക്ക് നല്ല ഗവേഷണത്തിൽ നല്ല ബന്ധമുണ്ട്. ദില്ലിയിലെ ഇന്ത്യൻ നാഷണൽ സയൻസ് അക്കാദമി കേരള മാത്സ് നടത്തിയ ധാരാളം പഠന ഗവേഷണങ്ങൾ ഞാൻ പരിശോധന വിഷയമാക്കിയിട്ടുണ്ട്. ഇത്രയും പറഞ്ഞുകൊണ്ട് CDC കോർഡിനേറ്റർ എന്ന രീതിയിൽ എന്നെ പരിഗണിച്ച
I think some net issues. Sir is not here.
Okay, fine. Thank you, sir, for your nice words and sorry for the inconvenience. I cordially invite Dr. Blumey Joseph, Head of the Department of Mathematics, to formally introduce and to welcome the key speaker, Dr. Manoj Kummini, to this event. Ma'am.
Okay. എനിക്കൊരു ബ്രേക്ക് വന്നിരുന്നു, ക്ഷമിക്കും. ഞാൻ ഈ പ്രോഗ്രാമിന് എല്ലാവിധ ആശംസകളും കോളേജിന്റെ വികസന സമിതിക്ക് വേണ്ടി നേരുന്നു. ഇത് വിജയകരമായ ഒരു പ്രോഗ്രാം ആകട്ടെ എന്ന് ആശംസിക്കുന്നു. താങ്ക് യു വെരി മച്ച്.
Thank you, sir. Thank you, sir. Now, good afternoon to all. A few words about our resource person, Dr. Manoj Kummini, Associate Professor, Chennai Mathematical Institute. Had his BTech in Electronics and Communication, Master of Engineering in Telecommunication Engineering from Indian Institute of Science, Bangalore. Post-graduation in Mathematics at University of Kansas, USA. PhD from University of Kansas, USA. And the topic of research is homological invariance of monomial and binomial ideals. His employment details includes postdoctoral fellow, Mathematical Science Research Institute, Berkeley, USA, during 2012. Research assistant professor, Purdue University, USA, from 2008 to 2011. Graduate teaching assistant, University of Kansas, USA, etc. Published many papers in international journals. He has done research talks at IIT Gandhinagar, IISER Pune, IIT Madras, Ramanujan Institute, Purdue University, USA, Indian Statistical Institute, University of Michigan, Northeastern University, Boston, Institute of Mathematical Sciences, University of California, City University of New York, University of Missouri, Columbia, Washington University, etc. He has given instructional lectures at Kerala School of Mathematics, IIT Bombay, Madurai Kamaraj University, University of Mysore, etc. He has done research visit at Purdue University, USA, American Institute of Mathematics, Northeastern University, Boston, etc. He has got Matrix Grant, National Board of Higher Education India Travel Grant. Add-ons different positions like co-organizer of ATM workshop on positive characteristic method in commutative algebra, IIT Bombay, co-organizer of workshop Sahadri Constance, Chennai Mathematical Institute, co-organizer of India UK seminar, etc. On behalf of all, I welcome Dr. Manoj Kummini for the presentation. Sir, please.
Thank you. Thank you for the nice introduction. Thank you for the invitation to speak in this seminar series. So I will speak about group actions and some applications. This is sort of a topic that one learns after getting familiar with groups. And one reason why one would like to understand group actions is that it appears in various contexts, not necessarily related to groups. And because of this, I will also show an application to graph theory from the ideas about group actions towards the end of the talk. Okay. So this is the plan for the talk. We will start with an example because but it would be useful for us to have some example in our mind when we see the definitions. So then we'll see the definitions and the basic terminology in the context of group actions. And then we will discuss a theorem called the orbit stabilizer theorem. That is a theorem that's most commonly used, and it is also not very difficult to visualize the theorem or prove it. So that's what we will see next. And we will use all of these things to understand the question about graph automorphism. I will define these things as we go along. And if there are any questions, feel free to interrupt me. I will be able to answer them as much as I can. Okay, so let's start with an example. So what we have here is an equilateral triangle with the vertices marked 1, 2, and 3. 1 is in this right corner, 2 is the one above, and 3 is on the left corner. And what we would like to see is the permutation group S3 on 3 letters. We would like to see a way the permutation group acts on this equilateral triangle. So what it does is we would use S3 to permute the vertices. So let's look at one example. So in cycle notation, we will write sigma as 1, 2, 3. So what does cycle notation mean in writing permutation groups? This means that the permutation takes 1 to 2, 2 to 3, and then 3 to 1. That's what this is as a cycle. Okay, so I hope the figure, the letters written in green are visible. So this is the old equilateral triangle with 1, 2, and 3 in black written as it was in the previous page. Okay, so now under the action, what sigma does is to change 1 to 2, 2 to 3, and 3 to 1. So that's what we would have after applying sigma is what I have written here in green. So the right corner, the bottom is 2, the top corner is 3, and the left corner at the bottom is 1. So this is the same as rotating the triangle, equilateral triangle, clockwise by 120 degrees, 2 pi divided by 3. So this is what sigma did is to rotate the figure by 2 pi over 3. So now let's look at another element of the permutation group. Okay, so let's call it tau. Okay, tau is the cycle 1, 3, 2. In other words, 1 goes to 3, 3 goes to 2, and 2 goes to 1. So then 1 goes to, so again, we have just written down what happens in the figure. So the black one here is what it was originally. Now in green, it has become 3. Similarly, 2 has become 1 and 3 has become 2. And if you think about this, what we have done now is to counterclockwise rotation by 120 degrees. Okay, so this was the original picture, and we have just rotated it counterclockwise by 120 degrees. But that is also the same as clockwise rotation by 240 degrees, 2 pi over 3 and 4 pi over 3. Okay, and therefore we can think of this as sigma applied twice, sigma composed with sigma. That's clockwise rotate. Just recall that in the previous slide we saw that sigma brings about clockwise rotation by 120, and now tau brings about clockwise rotation by 240, so that we can think of it as sigma being applied twice consecutively. So it's a composition. Okay, so this is what this is the underlying picture. We'll see a couple more permutations in what they do. Okay, so here we take a simpler, two cycle, 1, 2, and this just means that 1 and 2 are swapped, 1 goes to 2 and 2 goes to 1, and 3 is unchanged. Okay, so rho doesn't do anything to 3. Okay, so now if we go back and redo what happens, 3 is not changed. So in green and in black, I have written 3 here in the bottom left corner, and the top corner 2 became 1, and the bottom right corner 1 became 2. And if you think about this, this is reflection of the equilateral triangle by the line through 3 and the midpoint of the opposite edge 1, 2. So my figure is slightly inaccurate. This line should in fact be through the midpoint, but I hope that it is clear. At least I have written it here, that it's a reflection about the line through 3 and the midpoint of the edge 1, 2. Similarly, the cycles 1, 3 and 2, 2, 3 also give reflections. And it is not very difficult to work out what they are. So this is a very basic example of a group acting on some object. And we would like to sort of formalize this and then learn something about it and then try to use these ideas in a different context. So that's the plan for this talk. So as I said, this is an example of a group action on a set. The set is the equilateral triangle. Although we only discussed the vertices, we could have also have discussed a filled-in equilateral triangle and described rotation and reflection exactly as the way we have discussed here. Okay? So this is an S3 action on an equilateral triangle. So now, are there any questions about on the example that we just discussed? Okay, then let's. Okay, then let's move on to the definitions and trying to formulate these ideas that we just saw. Okay, so what we have is a group G, and X is a set. Okay, so think of G as the S3 from the example, and X as the equilateral triangle. Okay, so we will, just for convenience, we will usually write G multiplicatively so that the binary operation will be written as just a product. This is just a convention. It's not even a convention, it's just for our convenience now. Okay, and identity element of the group will be denoted as 1. Additive groups also will act there will be context when additive groups also act, but just for the talk, I will write them multiplicatively with identity element as 1. Okay. So now, what do we mean by saying G acts on X? So this is the definition. We say that G acts on X if for every G in G, there exists a map phi G from X to itself satisfying the following. Okay. So at least we will describe what the following conditions are, but what the conditions are, but at least let's make sure that we understand that this is what we did. For every group element, we had a function from the set to itself, from the equilateral triangle to itself. Okay, so this is what the conditions are. Let's look at it now. the map corresponding to 1. Okay, this one here is the one here is the identity element of the group. Okay, so remember, for every group element there has to be a map. For G there has to be a map phi G. So for 1, the corresponding map is the identity map on X. In other words, the function from X to itself that takes a point, an element little x to itself. Okay, so this is what we write as the identity map, and we will use this notation, ID subscript a set, to denote this map. Okay, so this is the first condition. And second condition is that in the group G there is the binary operation which we wrote as multiplication. So G and H are group elements here, and we look at what is the map phi corresponding to the product GH, and it should satisfy the property that it is the composition of the maps phi G with phi H. Okay, so phi H would be applied first, and then to its output phi G would be applied. So we will so that's the way we have written here. So on an element little x, we will take phi H x, and then to that we will apply phi G. So these two are the two conditions that we want this function phi G, the collection of functions phi G, to satisfy. Remember, for each group element there is a phi G. Okay, so in the previous example, okay, phi tau was clockwise rotation by 240 degrees. So maybe I'll just go back to the example here. Yeah, here, this was tau. So phi tau was clockwise rotation by 240 degrees. And that is doing clockwise rotation by 120 degrees twice in succession. And each of them is phi sigma. Okay, so in that example, phi tau is clockwise rotation by 240 degrees, which is phi sigma composed with phi sigma. Okay, so this is what we mean. This is what we meant. So in that example, this condition 2 was implicit. Okay. So now let's try to understand these two conditions a little bit more carefully. Okay. So take a group element G. Now in the group, G has an inverse. So 1 is equal to G inverse. That's also equal to G inverse G. So if you apply the condition 2 to this setup, condition 2 says what happens, what is phi of a product of two group elements. So then it says phi of G composed with phi of G inverse is phi of G inverse. So this was condition 2. The leftmost equality here is condition 2. And G inverse is the identity element of the group. So that's 1. Okay, so phi of 1 is identity of X. That was condition 1. Okay. And then doing the same thing on the other side, we would get phi G inverse composed with phi G. Okay, so this is the summary. Phi G composed with phi G inverse is the identity map on X, and it is also the composition in the other direction. So we have this picture. We have X here, and we have two functions, U and V. So this is the phi G and phi G inverse. Okay, so for convenience, for a reason, we will write it in opposite directions. Also, it's the same set X. That's because we want to discuss their composition. Okay. So U composed with V is identity map on X. So U composed with V is a map starting from the right side X. First apply V, come to the left, then apply U and come to the right again. Okay. So that's equal to identity X. Well, identity on the right side X, but they are the same set. Okay. And this is equal to V composed with U. So that means start from the left side, apply U, and then come back through V. It's identity here. So we have a pair of functions U comma V with this property. Okay. Now, so both composites are equal to identity. So U composed with V is identity, so it is injective. And sorry, I made it. Okay, this should have been V is injective. V is the first function, U is the second one. Okay, so if you have a composite of two functions that are injective, then the first function is injective. Okay, sorry, this should have been a V and not a U in the first line. Conclusion of the first line. Similarly, U composed with V is surjective, which implies that the second function U is surjective. Okay, so again, on the right side of these two implication signs, there is a typo. It should be V is injective and U is surjective. But anyway, this applies to both of them. So the conclusion is that both U and V are bijective. Okay. So now, so in other words, for each G, each group element, the corresponding map phi G is a bijective function from X to itself. Now, just as a remark, when we think about a bijective function, it's really a permutation. Okay? We don't, often the sets are not finite and they're probably not indexed by some 1 through n, but it is really a permutation of the elements of X. Okay, so just as an okay. So sometimes we might see the definition of a group action as an action of a group on X as giving permutations phi G of X, but it's equivalent to just saying giving functions satisfying those two properties. Okay, so the permutations have to satisfy this. And yeah, so before I get to the next definition, let me just add a remark here. So what we have really done is the set of permutations of X, or set of bijective functions from X to itself, is a group under composition, where the identity map, whether the identity element of that group is the identity map on X, identity function on X. Okay? So what we are doing when we give an action of G is to specify a group homomorphism from G to the group of permutations of X, or the group of bijective functions from X to itself. Okay? So that's really what we're doing, and these two conditions are really doing that. Okay? And specifying these two conditions says that we have now specified a group homomorphism from G to the group of bijective functions from X to itself. So that's another way of stating, giving the definition of a group acting on a set. Okay. So, are there any questions about these definitions, about groups acting on just the definition of a group action? We'll come back to an example after we make just a few more definitions. Okay. So we can think, so consider a group G acting on X. So what does that mean? So yes. Yeah.
Yes, Anna question.
Okay, thank you. Yeah. So what does that, we can think of it this way. So in the picture that we had sigma taking the corner 1 to some other thing, a corner 2 to corner 1, and so on. So we can think of the group as moving the elements of X in some way, and we'll see some examples where we can actually visualize them this way. But abstractly also, we can think of X as some sort of space in which the points of X are, the elements of X are the points, and the group just moves these points from one to the other. Okay? So suppose that, okay. So then, at least as a picture, we can think of the orbit of X, meaning what are all the points Y, which we can get as starting from X. Okay? So some phi of G of X is equal to Y. Okay? So the set of all such points is called the orbit of X. Okay? So it is the set which we will denote by ORB of X. The orbit of X is all the possible points phi G of X as G varies inside G. So all the possible points Y that can be reached from X by applying some group element. Okay? Some function, applying the function coming from a group element. Okay? So that's what's called the orbit of X. Okay, so now let's look at these examples. So I will introduce a couple more examples now to make these definitions clear. Okay, so in the earlier example of S3 acting on the triangle, equilateral triangle, the orbit of 1 is all 1, 2, and 3, because there is a cycle sigma which took 1 to 2, and there is a cycle tau which took 1 to 3. Okay, so both 2 and 3 are in the orbit of 1, and that's all the points. So that is the orbit. Okay. So we can get to 2 starting from 1 in some way, and we can get to 3 starting from 2, from 1 in by some other group element. Okay. So that's all the orbit. Okay. Now let's look at slightly slightly different example. Okay. So GL2R. So this is the invertible linear transformations from R2 to R2. Okay. We can think of it as 2 by 2 invertible matrices. Once we give bases for R2 and R2. Okay. So these are invertible linear transformations, and they act on R2 in a natural way, which is it's a linear transformation. So just apply to a vector. Okay. And GL2R, because these are functions from R2 to R, they will form a group. I mean, these are functions satisfying certain property. So they will form a group under composition, okay, which is the same thing. I mean, if you write elements of GL2R as matrices, then composition of function is same thing as matrix multiplication. Okay, so we can write them as matrices, and then matrix multiplication would be the group operation, and the identity element is the identity matrix, okay, the 2 by 2 identity matrix. Okay. So that's the action for GL2R on R2, the natural action of GL2R on R2. Okay, now let's look at what we mean by orbits of. Okay. So let's take maybe let's do the orbit of 0 first. So if you take the 0 vector in R2, then when you apply with any linear transformation, we will only get 0. Okay. Okay. So what we are doing is we take arbitrary linear transformations T in GL2R and take T of 0, apply the function T to 0, and but then there is just 0. So the orbit of 0 is a singleton containing just 0. Okay. But now let's look at a non-zero vector. So this is a property about vector spaces and invertible linear transformation, that if you start from a non-zero vector, okay, V, then given any non-zero W, there is a linear transformation which takes V to W. Okay. So this is a property about invertible linear transformations acting on vector space, and nothing to do with R2. It could be over any field and over any dimension, not necessarily 2 by 2. Okay. So given two non-zero vectors in a vector space, there is an invertible linear transformation taking one to the other. This is a general fact. So there exists such a T with this one. So in other words, all non-zero vectors form just one orbit, because you can go from any non-zero vector to any other non-zero vector by an invertible linear by multiplying by an invertible linear transformation. Okay. So therefore, the non-zero vectors form an orbit, and 0 alone is an orbit. So there are two orbits for the GL2 action on R2. Now let's look at another example. So this is a subgroup of GL2. This is the rotation by theta. So we will take now for this, just for this example 3, we will think of GL2R as 2 by 2 invertible matrices, because I would like to represent the rotation also by a matrix. Okay, so 1, 0 goes to cos theta sine theta, and 0, 1 goes to minus sine theta cos theta. So this is a rotation by theta in counterclockwise direction. Okay, so this is a group. Okay, this is a subgroup of GL2R because it's a group under composition. Identity matrix is here with theta equals 0. Okay, and G, the subgroup also, see, if a bigger group acts on some set X, subgroups also will act on the same set X. Okay, so G also acts on R2, and this is induced by the action of GL2R, which is a bigger group. So the smaller group also acts on R2. Okay, now let's look at the orbits are slightly different. If you take a non-zero vector, then TV, now T is a rotation by some angle theta between 0 and 2 pi. Okay. TV is a vector of the same length. Okay. So we can't start from, let's say, 1, 0 and get to 2, 0 by applying a linear transformation from this smaller group G. Okay. Therefore, there will be more orbits. In fact, given any two vectors of the same length, all that one needs to find is what is the angle between them, and then just rotate by that angle. We will go from one vector to the other. Okay. So if V and W have the same length R, so some R is a non-negative real number. If V and W have the same length R, okay, then we can always go from V to W by choosing a suitable rotation map. Remember, when we say we are thinking of R2 as a vector space, so all vectors are from 0 to some point inside R2. Okay, so we can go from any vector to any vector of some length to any other vector of the same length by a suitable T. So therefore, and we cannot change length by applying a T. So therefore, orbits are precisely characterized by the lengths of these vectors, and length is always a non-negative real number. So the orbits are precisely for each non-negative real number, take the collection of vectors of that length. Okay, this is what the orbits are. So this is one notion that comes from the idea of groups acting on sets. Okay, so there is a second notion called the stabilizer of X. So again, we now take a point little x in X. Okay, the stabilizer of X is, we define it as this set. Those group elements G such that phi gx is X. Phi g does not move X. So this is what we mean by the stabilizer. And okay, it is not very difficult to check that this is a subgroup of G. Okay. Yeah, sorry, I should have said the subgroup, this subgroup of G. Okay. Okay, I'll quickly just say why it is so. Suppose G and H, first of all, identity element of the group gives identity map on X. So that fixes every X, not just this given X. Okay? So that's clearly in the stabilizer in the set. And if we have two elements, G and H, if both phi G and phi H fix X, it does not move X, then the composite also will not move X. So for every G in G and H in G, for every G in the stabilizer and H in the stabilizer, the composite, the product is also in the stabilizer. Okay, so this way we can verify that the stabilizer is a subgroup of the group G. So this is, now let's go back to the three examples and try to understand what this means. So stabilizer of the point 1. Okay, so this means the group elements that don't that keep one fixed. Okay, this is this is generated by the 2 cycle 2, 3. Okay, similarly, the stabilizer of the element 2, the vertex 2, is the 2 cycle 1, 3, and the stabilizer of 3 is a 2 cycle 1, 2. Now, in the second example, where GL2 acts on R2, okay, stabilizer of 0 is the whole group. That's because every group element GL2, every element of GL2 fixes 0. Okay, this is what we are already written it some way. T of 0, T is 0 itself. So it comes from, okay, it's the same reasoning, which says the orbit of 0 is 0. Okay, in other words, so we'll see this in a few minutes, that it is related to this. Now, for V not equal to 0, the condition TV equals V. This is the condition that that specifies the element of the stabilizer. It's equivalent to saying that V is an eigenvector of T with eigenvalue 1. So let's just do one example. So let's say T. So we are trying to find the linear transformations T that fix 1, 0. Okay. So we want a linear transformation, 2 by 2 linear transformation. So we write it as ABCD. Okay, and then we wanted an invertible linear transformation. So we also specify that the determinant is non-zero. I mean, determinant of this 2 by 2 matrix is non-zero. Okay, and it should multiply 1 comma 0 and to give 1 comma 0. So in other words, it would say that A equals 1, C equals 0, okay, and then D not 0 to force the determinant non-zero. Okay, so stabilizer of 1 comma 0 is things of this form. Okay, B is an arbitrary real number, D is an arbitrary non-zero real number, and then the first column is just 1 and 0. Okay, so this is exactly the stabilizer of this vector 1 comma 0. And for other vectors, we'll have to do some calculation and figure out what the stabilizer is like. Now let's look at the third example, in which it is a rotation group. If V is not 0, okay, then any rotation will move V to something else, because it's rotation. Remember, the elements were indexed by the angle by which it rotates, and this is if you have two, I mean, if you have a non-zero angle, it will always move the vector. So stabilizer of any non-zero vector is just the identity map itself, nothing else. Okay? So it has a trivial stabilizer. Yeah, and if it's a zero vector, then stabilizer is a whole group, again for the same reason. Okay. So now, are there questions about this definition of orbit stabilizer or the examples? Okay, so now let's come to this useful result, not very difficult to prove, called the orbit stabilizer theorem. So the context is G acts on a group, on a set X, and we take a point little x in X. Then, okay, so we are claiming that there is a function. Then the assertion is that it's well defined and it's bijective. Okay. So on the one side, we are looking at the orbit of X, and on the other side, we are looking at the cosets modulo the stabilizer of X. We already observed that the stabilizer of X is a subgroup. It need not be a normal subgroup. So we only have the set of cosets, it's not a quotient group. It's not necessarily a quotient group. Okay, so G mod stabilizer X, and the square brackets G, by the square brackets G, I mean the coset of little g. Okay, modulo the stabilizer, the residue class or the equivalence class for the quotient action. Okay, so so this is by this square brackets G, we mean the coset of G. So now then we are claiming that there is a function from the coset of G that will give an element of the orbit of X, which is phi G of X. Okay. Remember, phi G of X is an element of the orbit by definition, and we are saying that this is a well-defined function, and I'll come to that in a minute, and it is bijective. Okay. So essentially, the orbits we can now think of as the set of cosets. That's what it's saying. Okay. So let me just briefly say why we are talking about well-definedness. See, we are trying to define a function on the set of cosets of a subgroup, okay, by picking an element of the coset. So we are trying to define on the set of cosets by defining something on G, by doing something to G. Okay, while we are, so if G and H have the same coset, then phi G should be, phi G and phi H should do the same thing to X. They need not be the same function, but phi G of X should be equal to phi H of X. So this is what I have written here. We need to check that this is independent of the choice of the element in the coset. So in our context, it means that we need to show that if G1 is equal to G2H for some H in the stabilizer, then phi G1X is equal to phi G2X. Okay. This is just the element, okay, not as functions. Phi G1 need not be the same function as phi G2. Okay. They may disagree at some other X prime, but on this X, they should take the same value. Okay. And in fact, this is not very difficult to check at all. So remember, G1 is G2H. So phi G1 is phi G2 composed with phi H. Okay. Now phi G1X is phi G2 of phi HX, but H is in the stabilizer, so phi HX is just X itself, and therefore we have equality. So therefore we have now defined a well-defined function from the set of cosets to the orbits, to the orbit of X. Okay, given an element, we are defining from G mod the stabilizer of that element to its orbit. We just have to check that it is bijective. Okay. So surjectivity is a little easier to check, so we will just check that quickly. We'll check that first. Okay, so take an element Y that's in the orbit of X. So what does that mean? It means that there is a group element G such that phi G of X is equal to Y. Okay. And then by definition of that function that we try to define, okay, phi G of X is equal to Y, and this function that we have just defined takes the coset of G, coset of little g, to phi G of X. Okay, that's coset of little g goes to Y. So it is surjective. Every element of the orbit of X is in the image of that function that we just defined. Now let's look at injectivity. Now suppose that the coset containing G1 and the coset containing G2 get mapped to the same element Y in the orbit of X. Okay. So what does that mean? It means that phi G1X is equal to phi G2X, and both are equal to Y. Now let's look at G1 inverse G2. So phi G1 inverse G2 of X is phi G1 inverse of phi G2 of X. But phi G2 of X is Y, so we substitute Y. But phi G1, remember phi is this is all bijective maps, and phi G1 inverse is the inverse function of phi G1. Okay, so then phi G1 inverse Y is X. Okay, so in other words, G1 inverse G2 is in the stabilizer of X, okay, and therefore call this the H. G2 is G1 times H. I mean this element here, G1 inverse G2, call it H, and then it satisfies this condition. So they both belong to the same. G1 and G2 have the same coset modulo the stabilizer. So this is a useful theorem. So for example, Silo theorems can be proved using these things. Okay. What is called class equation can be written down starting from this point. So we will not do any of the group theory applications with this. We'll try to do something else, okay, in this now. Okay, so we'll try to count. We'll try to use this theorem to help us count some things. So let's just review our current examples. G was S3 acting on an equilateral triangle. G has 6 elements. Orbit of 1 is 3 elements, okay, and the stabilizer of 1 has 2 elements. And the product of these two cardinalities is 6. So I mean, one consequence is, so when we say it's useful in counting, we typically mean in a finite group and finite set X. Okay. So one particular the number of cosets is equal to the order of G divided by the order of the stabilizer of X, and this theorem says it is bijective, so that is the cardinality of orbit of X. So in other words, order of G equals order of the stabilizer of X times the cardinality of the orbit of X. Okay. So that's a consequence from this theorem, and that's where we'll try to use it to count. Okay. So in this example, that's what we just said. Orbit has 3 elements, stabilizer has 2 elements, and and we see that 3 times 2 is 6, which is the size of the group. Okay. We can't use it in the other examples because they are all infinite. The X is R2, which is infinite. The group G is GL2R, which is also infinite. And it's not, I mean, there are other ways of quantifying how big they are, which will sort of agree with these calculations, but we will not, developing that requires more work and also more algebra behind it. So we will just use it in some finite context. Okay. So now we come to this this example. So we want to look at graph automorphisms. So graphs are something that all of us see some point. I mean, in various contexts. So whenever I say graph in this talk, I mean a finite simple graph. Okay, and we'll denote it by gamma because G we have already used it for groups. So we mean the following piece of data, which is a finite set of vertices. Okay, so that's the thing. That's a finite graph. The set of vertices is finite. And the second condition is a set of edges, and edges we mean v comma w, and v is not equal to w, and these are elements of v cross v. So this immediately forces that there are no loops, and then there are no multiple edges, because it's a subset of v cross v. I mean, some v comma w can occur only once. Okay, and there are no loops which we get by saying that v is not equal to w. Okay, just so these are not entirely required for describing the problem, but it just at least we will understand the simpler cases first if you need to proceed in this direction for more complicated situations. Okay, I mean for the need of defining group automorphism, we don't need to assume that it is finite simple. One could also allow for loops, or one could also allow for multiple edges. Sorry. Okay. Now, what do we mean by an automorphism of a graph? Okay. So it is a bijective map V to V that preserves the structure. In other words, if you take an edge V comma W, so V and W are elements of V, and V is not equal to W. That's what we are assuming. Okay. Finite simple graphs. If V comma W is an edge, if and only if, after applying this function, phi V comma phi W is also an edge. Okay. So it actually just it's a function phi which preserves not just the vertices but also the edges. So it preserves the structure of the graph as it is. Okay. So this is what we mean by an automorphism. Okay. And it is, yeah, we'll come to this. So let's look at an example. So we'll take a 4 cycle with 4 edges or 4 vertices, label them A, B, C, D like this. And we could take a function V to V, in which A goes to B, B goes to C, C goes to D, and D goes to A. And it is easy to check that this is an automorphism of gamma, meaning A comma B is an edge to start with. When you apply phi 1, it would become B comma C, and that's also an edge. Okay. No new edges have come, and okay, so it is a bijective function, not just from the set of vertices, but all the edges are also preserved. Phi 2 is, let's consider another one. A is not changed. A goes to A. B goes to D, C is unchanged, and D goes to B. So A is unchanged, C is unchanged, but B and D are swapped. Okay. That's also an automorphism because the edges are AB and AD. After this also we will get edges AB and AD. Okay. We just replaced B and D. Okay. I mean, just swapped B and D. Similarly, AB and BC are edges, and after we do this, after we apply phi 2, also B and BC and B, it would be DC and DA, but they will still be edges. Okay. Now let's look at another example, phi 3, in which A is fixed, B is fixed, and C and D are swapped. Okay, so C, instead of C here we call it D, and instead of D here we call it C. But then the edges have changed because now after applying phi 3, we would have an edge BD, but BD was not an edge to start with. Similarly, to start with, AD is an edge, but after we apply phi 3, AD is not an edge. Okay. So this is what, sorry, maybe I misspoke. AC is not an edge to start with, AD is an edge, but if you take AD and apply the function, we would get AC, but AC is not an edge. Okay. So this is, this phi 3 is not an automorphism of gamma. Okay. So now, one of the reasons why we study automorphisms of some structures is that if you identify all the different automorphic, all the different isomorphism classes, or in other words, all the different non-isomorphic things, it is sometimes easy to understand what the underlying structure is. Okay. So we typically, given a structure, we would like to understand its structure preserving bijective functions, and in many cases it would so happen that the set of automorphisms from gamma to itself, automorphisms of gamma form a group under composition, because these are functions. So the natural group operation is composition with identity element as identity map, identity function on the vertex set. So if you take the identity function vertex set, neither the edges nor the vertices are changed. So it's clearly preserves, it satisfies the definition of an automorphism. Okay. So I'll skip the proof. This is not very difficult proof. One has to sit and check these things, that the group under composition, everything is fine. Okay. That if, to start with, phi is a bijective function. And then we are putting some condition for it to be an automorphism of the group, the full graph structure. So then you can prove that the inverse function is also an automorphism. So a few things have to be checked, but nothing that is surprising. So I'll just skip the proof. Okay, we'll just, okay. So we'll write aut gamma for the group of automorphisms. So it is a set of automorphisms in which the group operation is composition. Now we ask, given a graph gamma, can we determine its automorphism group? So typically it will be used, given any structure, it would be useful to know what its automorphisms are, so that typically if you study two structures that are automorphic to each other, then that are isomorphic to each other, then they will also have the same properties. So it's a good, so now let's just go back to the for cycle. One can do it in slightly more complicated examples, but here at least we can say quite a bit. So this is a starting point for understanding this. Okay, so as we said earlier, automorphism group of a graph is the set of automorphisms is a group under composition, and it acts on this whole set gamma v comma e. So it acts on V, and compatibly it acts on E. So this sort of action is also sometimes sometimes quite common. There are two sets in question, and the action between them is in some way compatible with each other. Okay? So here it means that vertices are moved, and then the edges are also moved in the same way. Okay. So now gamma, for now we'll just consider the for cycle. And from the orbit stabilizer theorem, what can we say about, so we are going to apply the orbit stabilizer theorem to aut gamma by looking at various situations. Okay, so this we observed earlier, the order of the group is the cardinality of the orbit times the order of the stabilizer. This is a consequence of the consequence of the orbit stabilizer theorem. But we typically write this only for finite sets and finite groups. So now this is what we have. So we already saw one automorphism, which is phi1, which takes A to B, B to C, C to D, and D to A. If you apply phi1 composed with phi1, it will go from A to C and B to D and so on. Then phi1 composed with phi1 composed with phi1, it would go from A to D, B to A, C to B, and so on. So in other words, orbit of A is all the four vertices, A, B, C, and D. Okay. So using this, we now immediately see that automorphism group is 4 times the size of the automorphism group is 4 times the size of the stabilizer of A. Okay. Now, this is where the group structure. So far, what we have just said is, it's essentially we have only looked at, in the first half of the slide, we have only looked at the fact that automorphism is a bijective function on the, automorphisms are bijective functions on the set of vertices. So we can write something like this. But now we will use its relation to edges, which is, if you take an automorphism phi, and it stabilizes A, then it has to, it can only permute the neighbors of A, because otherwise some new non-existent, previously non-existent edge would now show up. Okay, so the neighbors of A, meaning those vertices from there to which there's an edge from A, between which there's an edge from A, must be preserved. So, okay, so if phi is an automorphism, it can, okay, so the stabilizer of A will act on the neighbors of A, which is just B and D. Remember, this is just B. Neighbors of A are just B and D. Okay? So the only thing it can do is it can swap B and D or keep them unchanged. Okay? But it cannot take C to D, because then the whole thing would be, it will not be an automorphism of this thing. Okay? So this is where we have used, the extra thing that the bijective function phi should move vertices and should move the edges in a compatible way. Therefore, it says that the stabilizer of A has two elements. Okay, I've cheated a little bit, but that it only says that stabilizer of A, there is a group homomorphism from stabilizer of A to the permutation set on two elements, but one can show that this is fine. Okay, so stabilizer of A has two elements. Okay, so in other words, the automorphism group has 8 elements. Okay, so just by using the theorem, without knowing anything about the group, we have now said that it has 8 elements, just by looking at the set X and the structure which is getting on which the group is acting. Okay, only thing we know is the X, the set on which it is acting. What is the structure of X? Nothing specific about the group, but we have already concluded that it has 8 elements. Okay, just by using this orbit stabilizer theorem. Okay, so now I would just like to clarify this a little bit. So a general observation is that, not necessarily related to this particular example that we are looking at, if a group acts on a set X, a G acts on a set X, then if you look at a conjugate of the stabilizer of X, okay, G times the stabilizer times G inverse, this is the stabilizer of G of X. Phi G of X. Okay, so a slight abuse of notation. By this I meant phi G applied to X. Okay. Therefore, the stabilizer is normal if and only if stabilizer of X is equal to stabilizer of Y for, I see, a lot of typos here, for all Y in the orbit of X, not stabilizer of X. Overall, okay. This should be, the last part here should be for all Y in the stabilizer of X. For all Y in the orbit of X. The two stabilizers should be, stabilizer of X should be same as stabilizer of Y. Okay, so in the example, stabilizer of 1 moves to the stabilizer of 1. It was. Okay. So stabilizer of 1 is not normal. Okay, you can swap B and D. Sorry, again, more typos. I apologize. I meant A, B, and not 1, 2, A, B. Stabilizer of 1, stabilizer of A moves B, okay, which is in the orbit of A. Okay. So they both don't have the same. 2 is the orbit of A, but stabilizer of A is not the same as stabilizer of B. So this is not normal. Okay. So in other words, odd gamma has a subgroup which is not normal. So odd gamma is not abelian. Okay. Again, all of this is just used from the description of group action sets. We have now concluded that odd gamma is not abelian. Then we have now used some more knowledge, which is that there are exactly 2 types of non-abelian groups of order 8, which are quaternion group and then the dihedral group 8 elements. And then a little bit more work. There are in fact 4 non-normal subgroups of order 2. Okay, quaternion group has only 1, so this is not quaternion group. Okay, so the automorphism group is in fact D8. Okay, dihedral group on 8 elements. So again, the last part of the conclusion, we may not be able to do it for arbitrary graphs gamma. We may not be able to determine, just by looking at the orbit stabilizer theorem and various notions related to group actions, we may not be able to determine odd gamma completely, but we can definitely get some information about this. Okay, so this is an application in an area that is not directly related to group theory. Okay, in some sense, abstract group theory. Okay. Okay, so I will stop here, and thank you. And if you have questions, I can try to answer them.
Thank you, sir, for the session. Anissa, is there any question?
Yes, Miss. Sir, first question.
Yeah.
Can we have stabilizers in infinite dimension?
Yes, it is possible that, I mean, for example, this the stabilizer of sorry, I forgot where the example was. Okay, anyway, sorry. Yeah, the stabilizer of a point for GL2 action on R2, say stabilizer of 1, 0, that's a 2 by 2 matrix with 1, 0 as the first column, then arbitrary B on the top right element, and D is a non-zero thing. So it is, I mean, it is essentially R cross the non-zero elements of R. And it is, I mean, yeah, so there are such infinite sets. So that depends on the group and the set on which it is acting.
Thank you, sir.
Okay, I hope it is clear.
Anissa, next question.
Sir, it's okay, clear. Next question. Is there exists a generator for stabilizer? Is it possible to develop such a generator under some conditions?
No, I think in generality, I think it might be difficult. It might be possible in specific problems, I think. But I think in general, it might not be very easy to describe a generating set for the stabilizer.
Okay, sir. Next question. Is stabilizer possible only for permutation groups?
No. It's maybe no. In this example of maybe it was here. Okay. Yeah. So no, this example we are discussing, the example 2 here, we're discussing GL2R acting on some vector space. I know it has a stabilizer. So it is just it's a property of an abstract group acting on a set. Just the only thing that we need to know is that the group needs to act on a set by as bijective functions. That's all. It can there will be a notion of a stabilizer orbit, etc. Not necessarily permutation groups. I could do only those things because in finite case we can always represent them by some subgroup of a permutation group. So the examples I chose, because they were finite, I had to do. They all appear as if we were working only with permutations, but in any case, that's every finite group is a subgroup of a permutation group, so we can treat them as permutations. Yeah.
Okay,
is that
sir.
clear? Yeah. Okay.
Okay.
Okay,
Sir, next question.
One more question,
Hello.
Yes, Anissa. Yes.
Under which condition a stabilizer become normal?
So I mentioned it here without proof. Proofs request some thinking, but not again. This is a very basic. Yeah. So the key point is this: conjugates of the stabilizer. So G times stabilizer of X times G inverse is the stabilizer of phi of G of X. I sort of abused a little notation here. I called it G of X, but what I meant is phi of G of X. Okay. So because of this, if this is normal, if stabilizer of X is normal, then it would say that stabilizer of X is equal to the stabilizer of phi of G of X. Okay. This is true for every G. So in other words, for every Y in the orbit of X, stabilizer of X is equal to stabilizer of Y. Okay. And this is when it is normal. Okay. So here there's again a typo. I meant for every Y in the orbit of X. Okay. Stabilizer of Y is same as stabilizer of X. Is that clear? This is.
Okay, sir, clear.
Yeah, yeah.
One more question is there from Kusum Rajbar. If we know automorphism of subgraph, what can we say about automorphism of graph?
So that's not much directly, because substructures could have considerably bigger, considerably more automorphisms than the whole thing. So it is not very easy to describe, to compare those two things. Okay. So for example, if you take, let's say the simplest case is an edge, subgraph of the edge between 2 points. Now there are only two automorphisms. I mean, yeah, it's just S2. It's just permuting those two edges. But that may not be compatible with an automorphism of the larger group graph, because this depends on the degrees of these vertices, etc. So suppose there is a vertex of degree 3 and a vertex of degree 4, then for the larger graph, there will not be an automorphism in which these two vertices are interchanged, because they don't have the same degrees. But on the other hand, if you just consider a subgraph consisting of these two vertices, then it is just an edge, and then there is an S2 acting on it. So there may not be any compatibility between automorphism of a substructure and the automorphism of a larger structure.
Okay, thank
Is
you,
that
sir.
clear? Yeah, yeah.
Sir, one more question. Can I ask? We
Yeah,
received one more questions.
yeah.
Under which condition a stabilizer become abelian?
I don't know an answer. It may be specific. In specific cases, it might be true, but I don't. There is no general reason why the stabilizer should be abelian. Okay? So in the examples that we saw, the stabilizers were abelian, I think. So that's me. So again, there might be something specific to the example in question where it became abelian, but not in general. There is no general result, as far as I know, which tells us when stabilizer would be abelian.
Okay, sir. Thank you.
Yeah. Yeah. Maybe in this example, no, this is also not abelian. Maybe it is, but yeah. So, but there is no general principle on why a stabilizer should be abelian.
Okay, sir. Thank you.
Sir.
Anissa? Anissa?
Ma'am.
Yes.
Hello, ma'am. Good afternoon, all. നമ്മൾ ഇപ്പോൾ ഗ്രൂപ്പ് ആക്ഷൻസ് ആൻഡ് സം ആപ്ലിക്കേഷൻ എന്ന് പറയുന്ന ടോപ്പിക്കിനെ ബേസ് ചെയ്തിട്ട് സാറ് വളരെ നല്ലൊരു ടോക്കാണ് നമുക്ക് തന്നത്. ഒത്തിരി വലിച്ചു നീട്ടാണ്ട് തന്നെ ഒരു ഡെഫിനിഷൻ പറഞ്ഞിട്ട് അതിന് എക്സാമ്പിളും പറഞ്ഞ് നമ്മളെ ഒത്തിരി ബോറടിപ്പിക്കാണ്ട് പെട്ടെന്ന് സാറ് വൈൻഡ് അപ്പ് ചെയ്തു. ഒത്തിരി കാര്യങ്ങൾ പുതിയതായിട്ട് അറിയാൻ പറ്റി. ഓർബിറ്റ്, സ്റ്റെബിലൈസർ, ഓട്ടോമോർഫിസം, അങ്ങനെ ഒത്തിരി കാര്യങ്ങളിൽ നിന്ന് പഠിക്കാൻ പറ്റി. സാറ് നന്നായിട്ടാണ്, നല്ല രീതിയിലാണ് ക്ലാസ് എടുത്ത് തന്നത്. ഇത്ര നേരം ഞങ്ങൾക്ക് വേണ്ടി ചെലവഴിച്ചതിന് വളരെ നന്ദി പറയാണ് സാർ. സോ താങ്ക് യു സർ.
Thank you.
Thank you, sir, for the wonderful session. Next, I would like to invite Mr. Sriraj KS, Assistant Professor of Mathematics, to deliver the vote of thanks.
Good afternoon to all. I'm very happy to express our gratitude to all of you. First of all, I would like to thank Dr. Manoj Kummini, Assistant Professor, Chennai Mathematical Institute, for spending your valuable time with us. Actually, it was a very nice talk. He explains, he reveals the interplay between the graph theory and algebra. As a researcher in algebraic graph theory, it was a very nice talk, and it reveals all the how we can apply the idea in algebra in graph theory, and conversely, we can also apply the some concepts in graph theory in algebra also. So we are very thank you, sir, for your nice talk and also spending a valuable time with us. Thank you, sir.
Thank you.
Next, Next, I would like to thank Dr. Vinod Kumar, CDC coordinator of Maharaja's College, for his felicitating talk. Thank you, Vinod Kumar sir. Next, I would like to thank our head of the department and convener of this program. As all of you know, this is the 9th talk in our webinar series. So she is the brain of this program, and all of you can expect how much effort she's put to conduct such a webinar series. So thank you, ma'am. Next, I would like to thank our coordinator of this webinar series, Ms. Mary, Assistant Professor of Department of Mathematics. With the convener, she put a very great effort to conduct such for the smooth conduct of this program. Thank you, Ms. Mary. And our principal, Matthew George sir, for his valuable advice and suggestions for conducting this program, and other faculties of the department and the research scholars, especially Sri Devi, for the technical support. And the success of every program depends on the participants. The program becomes a success because all of you. So I would like to thank all the participants also, and the PG students for your support. Okay, thank you. Thank you all of you.
Thank you, Sriraj sir. Once again, thank you all.
Thank you, sir.
Thank you.
Thank you, sir. With this, we conclude our today's session.
Thank you.
Thank you, sir.